Part B, we focused on using a singular CSTR to model both material and energy balance. In Part C, we took the material balance of Part A a step further in creating a series of tanks. And Part D, which is now, it makes sense then that we'd kind of combine Part B and C and divide Part B as a continuous stirred tank reactor into 20 smaller tanks to mimic flow reaction. So that's the goal of this video, and it should be pretty quick considering we're using Part B. Now, the goal here is primarily to use a little bit of indexing in Python, and that's going to be the hardest part of this, is ensuring that we're keeping the right numbers in check here. So let's go back to our Part B, and what we really want to do here is we want to ensure that, let's see that this is running. Okay. Turning this down. Okay. So the first thing that we're going to go ahead and do is split this into 20 tanks. Now, there's a couple of these givens that are going to be changed here. For example, we're going to want to divide our volume for each tank by n. Similarly, some other things that we're going to want to divide here. Let's see if there's anything else. UA should be divided by n for each tank. And our initial temperature again is going to be that 338.5. Now, to structure our initial conditions, we want to simulate 20 tanks at steady state now instead of just one, so we can use an array to do this. For CA naught, we can just say NP pool for n 0.5, right? Similarly, for T naught, we can do the same thing. Awesome. And now, let's see. It might help us to just have an initial conditions vector. And so that's what I'm going to do here, is just row concatenate. Let's see. Do I use that, or do I use that? I think that one. So let's concatenate CA naught and T naught. Object is not callable. Here are my imports. np.log. Oh, maybe I'm supposed to use brackets? Question mark? Okay, awesome. So now the next step here is going to be to define kind of the conditions that we want to keep constant as functions. So I'm just going to do that right here above our balance functions from earlier. So I'm going to call the first one Cin of t, and what that is, if we go back to our problem statement here, we can see that we want our concentration to be constant at 1 molar and constant temperature at 338.5. So let's go ahead and do that then. We want to go ahead and return 1 molar of concentration. And we can do the same thing then to have a function of temperature in T, and we're going to return 338.5. That's what it says. It's Kelvin. Okay. So now we've gone ahead and defined our functions here. This is our balances from earlier. So now our vector that we're putting in is going to be a function of concentration and temperature, so we split that. Awesome. That's just splitting it right down the middle. And the next thing that we're going to want to do is, let's see, K. So T here is now a vector. We'll have to keep watch of that, which means we'll have to iterate K here. Okay, so similarly to part C, our tanks, the first tanks in the process, are going to kind of get a special denotation here. So, let's see, let's call this, let's shorten this, MB1. I think would probably, maybe MB0 would be best for this guy here. And then let's go ahead and call in our function for concentration. I should put a C in, minus CA, and we want that to be the very first value. K should be the very first value, and then CA should be the very first value. Okay, and then we're going to go ahead and have to define MB for the rest of them, right? And so that would just be Q over V times, now instead of C in, we should be calling our concentration value, let's think, it would be from the very beginning all the way to the last one. So that's going to be that indexing in Python, and subtract, well, so this is what's going out of the tank. So out of tank 2 all the way to the end. Okay. And then our reaction here, so K should follow the indexing of what's coming out, just as it did in part C, and same for CA. Let's do the same thing for the energy balance then. Let's call this EB0 now, just so it's easier to find. MB0, MB, EB0, EB. Okay. And we're going to want to row concatenate these. So then, let's see, T in is going to be our function here, minus temperature of 0, K of 0, CA of 0, and then T of 0 here. Okay. Similarly for EB, it's going to be virtually the same formula. So what's coming into this tank is going to be what's going out of the last one. So T from the very first T to the end, I believe. Yeah, that sounds right. We'll try it and see what works. Minus T, and this should be from the second one to the end. Okay. Plus meg H reaction times, again, K should be from 1 to the end here, and then multiplying that by CA 1 to the end there, and then divided by C times rho minus UA, which is now reactor specific, C times rho times V. Okay. C times rho times V times T, and again, so we want the end, minus TC naught, assuming the cooling water temperature doesn't change. Okay, so there's our balances function. We shouldn't need balances 2 anymore. Now, let's see what we want to do next. I'm going to solve IVP. So solve IVP. Let's do balances from, okay, we want to go ahead and define a T end here first. So it's 2 minutes. So balances and then 0 to T end, and then do it for our initial conditions here, and then method, of course, is going to be dough and dense output equals true. Okay, so it converges. All right, we got to the end, so let's store that in res. Okay, so now we have to be really careful. First, we're in our plot. So I'm going to start with my for loop, for I in range n. So for each tang, we want to plot. I know I haven't defined fate yet, but I'm just going while I'm hot. So x will be whatever I make my t plot, and then y will be c plot from for I. So I will start at 1 and go to the end. So that's what I want. And then obviously mode is going to be lines and row equals 1. So I'm going to have to make big equals make subplots rows equals 1, columns equals 2, and I'll say row equals 1, column equals 1 for concentration, and then I'll go ahead and say let's give it a name, I guess. I guess an F string. That would be CA. It would just be I, maybe I plus 1. We'll see. So same thing then here, except we just have T. T plot and TI. Okay, and obviously we'd have to do our fake dot update layout, all that garbage. Equals 400. Template equals probably underscore dark. Okay, so now we got to define plotting points here. Okay, so we found res. Res is what? Let's look at res.y. Okay, so then what we want to do is define, obviously, a time plot as the lin space from 0 to t end with like 100 points, right? And then, okay, how do we want to split? We just want to split res.y over the t plot. So c plot is first, and then T plot is second. It's going to be NP dot split of res dot solve for T plot. This makes sense. Oh wait, split it into two pieces. Oh, so close, so close. Okay. So, this is definitely, oh, put it on the same column. Now it's all right. Almost there. Maybe I need to do an extra step. No. Axes would all be the way. Where did I go wrong here? Is the question in the plotting. That looks pretty right. Plot. Something's wrong here. Oh, I have the commas here. There we go. That's starting to look better. Actually, I think it's right. Let's look at it. So, our concentration profiles are dipping after they jump at about time equals 1. Okay. Yes. Okay. I think we're in the right spot here. So, is this what we would expect? Is always the question. So, we can see that the temperature profiles here have quite a vast axis on the y side, which is interesting. So let's look at, for example, okay, cool. So let's look at one reactor. So this is the very first reactor, right? So initially we had it at 0.5 concentration, and then we raised it. As we raised concentration, obviously the temperature raised kind of a little bit retroactively, right? Because the reaction is taking place. We know the reaction is exothermic because of its negative HR value. And so as the temperature goes up way more, we lose all of our concentration very, very quickly. So then that temperature is then going to cascade into the next reactor. So really, I think in 2 minutes, we're really just seeing kind of the full reaction of those first two. If we were to extend our simulation here a little bit longer, then again, okay, so concentrations are all going to drop off really quick, but you're going to see, oh, maybe not that long. Let's go for 5 minutes. Okay, so here's something a little bit more interesting. So concentrations are kind of dropping off around the same amount, but you're having temperature rise in sort of that characteristic way, right? So the temperature should rise after the concentration falls, because as the concentration is falling, it's creating more energy and increasing the reaction, right? And that's what we modeled exactly right here in this term in our energy balance. But subsequently, because we're looking at these reactors in series, the temperature is also affecting the next one, right? In all of this indexing that we did. In fact, that was the exact goal of indexing it in that way, is to ensure that the temperature was being propagated throughout the series. So let's go back to 2 minutes here. There we are. So again, this one's much more pretty because we can see exactly how it's reacting very clearly, and how that concentration is being pushed then into the next reactor. So throughout these 4 videos, we basically just did a complete review of material and energy balance. We looked at how to simulate different systems, and from a material perspective, and then subsequently then from an energy perspective, and then how to take that knowledge and apply it to a more rigorous coding example where we had 20 reactors in series. So in the next set of videos, I hope to kind of take these principles even further in being able to simulate and figure out exactly what it means for a system to be stable. So we've seen how systems can react, right? And we would say, well, there's probably some instability happening here. Well, what do we mean by that? And when can we quantifiably say that a system is stable? These are the questions that I hope to answer next time. That's all for now. Bye-bye.